Pericyclic reactions. So what are pericyclic reactions? Let us see what are pericyclic reactions. So we know the mechanism of a large number of reactions. Many of them proceed either by a polar mechanism or a free radical mechanism. But there are a group of different reactions which does not proceed either by polar mechanism or by a free radical mechanism. So many attempts were made to isolate, trap, or detect the intermediates involved in these reactions. So all those attempts were unsuccessful. So examples of such reactions are Diels-Alder reaction. So a Diels-Alder reaction involves 1,4 addition of substituted alkene to a conjugated diene. So this type of reactions are concerted. So the electronic rearrangements involved in bond making and bond breaking proceed simultaneously in a single step. And many of these reactions are reversible and the equilibrium lies well over to one side or other side of the reactions. So the term pericyclic has been used to describe such concerted reactions that proceed via a cyclic transition state. So I repeat, the term pericyclic has been used to describe such concerted reactions that proceed via a cyclic transition state. So further, the pericyclic reactions are mostly unaffected by polar reagents, solvent changes, free radical initiators, and other changes in the course of reactions, but they are influenced by the heat or light. So when pericyclic reactions are carried out under thermal conditions, they give one type of product, and under photochemical conditions, they give a different type of product. And some photochemical reactions occur only under thermal conditions, while the other one can occur only under photochemical conditions. So that means the pericyclic reactions are influenced only by heat or light. So for example, we have seen earlier the Diels-Alder reaction. So it is a reaction which can occur only under thermal conditions and it fails to occur under photochemical conditions. So whereas if we take the concerted combination of two molecules of ethylene to form a cyclobutane, so this reaction occurs only under photochemical conditions and fails to occur under thermal conditions. So therefore, the thermal and photochemical effects, so they also affect in the formation of different stereoisomers of the product. So for example, if we take the cyclization, electrocyclization of trans-cis-trans 2,4,6-octatriene. So this reaction under thermal condition gives a cis product, and under photochemical conditions, it gives a trans product. So we can see here, this is trans-cis-trans 2,4,6-octatriene. So the geometry of the double bonds is trans, this double bond is trans, this is cis, this is trans. So when this reactant is subjected to heating, so it results in the formation of cis-1,2-dimethyl cyclohexathreephi diene, and in this product the two methyl groups are cis to each other. So whereas the same reactant under photochemical irradiation results in the formation of trans-1,2-dimethyl cyclohexathreephi diene. So that means the thermal and photochemical reactions, they result in different stereoisomers of the product. So like that, the pericyclic reactions are influenced only by heat or light. They are not influenced by the solvent changes, free radical, initiator, and the ionic reagents. And many of these reactions are reversible and the equilibrium lies well over to one side or other side of the reaction. So the pericyclic reactions, now let us see how these pericyclic reactions are classified. So mostly pericyclic reactions are classified into three types. So they are cycloaddition, electrocyclic reactions, and sigmatropic reactions. A cycloaddition reaction involves the concerted combinations of two molecules of olefins, so to form a cyclic compound. So earlier we have seen Diels-Alder example. So where a diene reacts with a dienophile to give the cyclohexene. Similarly, the concerted combination of two molecules of ethylene to form cyclobutane. It is also considered as a cycloaddition reaction. So here two reactants are involved. If one reactant contains m pi electrons and if the other reactant contains n number of pi electrons, so the product contains m plus n minus 4 pi electrons with two new additional sigma bonds. That means the two pi bonds are converted into two new sigma bonds in the product. So this is one type of pericyclic reaction. So the second one is a electrocyclic reaction. So in a electrocyclic reaction, only one reactant is involved. And in these reactions, a sigma bond is formed at the termini of a conjugated pi system. And in this reaction, a sigma bond in the acyclic compound is converted into the pi bond in the acyclic compound is converted into a sigma bond in the product. So if we see the acyclic compound, if it contains n number of pi electrons, its cyclic partner contains n minus 2 pi electrons with one additional sigma bond. So therefore, in a acyclic conjugated system, a sigma bond is formed at the termini of a conjugated pi system in an electrocyclic reaction. So the example is cyclization of trans cis trans 2,4,6 octatriene. So under thermal conditions, as we have seen earlier, this cyclization reaction results in the formation of a cis product. Under photochemical condition, the same reactant gives a trans product. So it is an example of an electrocyclic reaction. Similarly, the electrocyclic ring opening. So electrocyclic ring opening. Here the forward reaction is the electrocyclic ring opening and reverse reaction is electrocyclic ring closure. In the case of 1,1-dimethyl cyclobutene. So on electrocyclic ring opening, it results in 1,1-dimethyl 1,3-butadiene. So it is an example of electrocyclic ring opening. So this example which we have seen here, the cyclization of trans cis trans 2,4,6 octatriene is an example for electrocyclic ring closure. And here also the reverse reaction is example of electrocyclic ring opening. So the third type of pericyclic reactions are sigmatropic reactions. So it is a reaction in which a sigma bond flanked by one or more pi electron systems shifts to a position is called a sigmatropic reactions. So these reactions are classified by putting two numbers in brackets. So these numbers refer to the relative distance in terms of atom each end of the migrating sigma bond has moved. So for example, here G is the migrating group. It is a pi system. It is a monoene. So in this case, the G, which is migrating group, migrates from this atom to this atom. That means it moves by 1, 2, 3 atoms. So from C1 carbon, it moves to C3 carbon and the pi bond will shift in the opposite direction. That means the migration of sigma bond is followed by a shift of the pi bond in the opposite direction. So since the migrating group is moving by 3 atoms, it is called 1,3 sigmatropic reaction. And here we can see this is a diene. This is a diene with 1, 2, 3, 4, 5 carbons. The migrating group is present here. So now we number the system from the carbon containing migrating group. So 1, 2, 3, 4, 5. And in this case, this migrating group moves from C1 to this C5. And the pi bonds will shift in the opposite direction. And it is an example of a 1,5 sigmatropic reaction. So therefore, in a sigmatropic reaction, a group migrates along with its sigma bond by certain number of carbon atoms in a pi system, So very often this migrating sigma bond is placed in between two pi systems. And the examples of such reactions are Cope and Claisen rearrangements. So here we can see it is 1, 2, 3, 4, 5, 1,5 diene. It is a 1,5 diene. And here this sigma bond moves from this position to this position. So this end of sigma bond moves by 1, 2, 3 atoms. And this end moves by 1, 2, 3 atoms. And therefore, it is an example of a 3,3 sigmatropic reaction because each end of the migrating sigma bond moves by 3 atoms. And sometimes in this pi system, oxygen atom may be incorporated. Oxygen atom may be placed in between two pi systems. So we can see here an oxygen atom is present in between two pi systems, and this is the migrating sigma bond which moves by 1, 2, 3 atoms, and this end moves by 1, 2, 3 atoms. So it is also a 3,3 sigmatropic reaction with the oxygen atom in between two pi systems, and this type of reaction is called the Claisen rearrangement. And in this case, this vinyl allyl ether or allyl vinyl ether is converted into 1-pentanol. 1-pentanol. And it is called Claisen rearrangement. And in this case, all the atoms are carbons, and it is called Cope rearrangement. And both reactions, both Cope and Claisen rearrangement reactions occur under thermal conditions. The fourth type of pericyclic reaction is group transfer or in reaction. Here we have two pi systems. So a atom or a group or a hydrogen atom, let us say a hydrogen or an atom or a group migrates from one system to the other system, and the two systems are joined by a sigma bond. So for example, here we can see this is 1-propene and this is the allyl hydrogen. The allyl hydrogen, it migrates to the monoene, and a sigma bond is formed between the two pi systems, and this pi bond is migrating from one position to the other position. So this type of reactions are called group transfer reactions. This is also another type of pericyclic reaction. So thus pericyclic reactions are classified into 4 types: cycloadditions, electrocyclic reactions, sigmatropic reactions, and group transfer or in reactions.